So, these are the data. So these are the data that I got, okay? So I plot in this way, and the only I did was just plot the time and plot the value, okay? So value close, value open, okay. Now my goal is to make a prediction, because my goal is to have a very easy life, right? Oh, by the way, let me show you this, okay? So, we were discussing all that. Now, so let's make it, okay? This is the command window. So if you never use, everything you write, you need to write here. Now, what I'm going to do is, the goal was to, right. Okay, so let's do it, So I write a matrix, and I don't know, I write a size like a matrix of 200. Now, rand 200 by 200, this is the size of a matrix, this is square, okay? So I generate a matrix. Now this is the workspace, and the workspace is telling you that the matrix is generated is 200 by 200, okay? So, I go back, can you see everything? Okay, so you see what I see. Now, I generate a symmetric matrix, which is, I said A is equal to B plus B prime, which is a transpose, I close the bracket, divide by 2, and then I put another bracket there. Okay, in this way, I create a symmetric matrix. Now, I need to calculate the eigenvector. Now, I always forget what is the instruction, so I make help. Help is, is giving you the syntax of the MATLAB instruction, of the MATLAB function. Okay, so blah 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 blah. But so if I have a matrix, there is a column vector containing the eigenvalues. If I make this way, then you need always to look at. So it's V. So if I write A is square V comma D, which means in V matrix, okay, the diagonal entry is D. So in D there are the eigenvalues organized in the diagonal form, and in V there is the eigenvectors. Okay. Now it tells you the syntax. The syntax is the following. A multiplied by V is equal to V multiplied by D. Now, when you need to understand what is the form, what is the organization of the data of the specific eigen decomposition, look always the way, the notation that MATLAB is using. MATLAB is an example, but you can use Fortran, you can use C, C++, you can use Solver, you can use whatever, okay? So Python, it depends on the system that you are looking at. So they're all the same. Beyond the way, the basic syntax, all the software, the basic function are all the same. So what I need to use, actually, that would be enough for me to get E. Because E, is exactly the eigenvector. Where is it? So Q, what I want is the eigenvector. So I can simply make the assignment of A to another matrix, which is called Q, okay, to simplify. On the other hand, if I look at the matrix, if I look at the matrix, what was the matrix A? Okay, this is the matrix, you see? It's a set of values. It's 100 by 100. It's not a picture. I could have taken the picture, for instance, okay? And the results will be the same, Of course, if I take a picture, then the image is a picture. By the way, it is symmetric, but you don't see it. Now, since, I don't know, let's continue with this color code. Now, I want to create the eigenvector. Q is equal to A. Okay, in this way, yeah, I need to put, it's better to put this termination in order to avoid that every time you make an instruction, I mean, you don't have all the numbers appear in the screen, okay, which is Q. Now, you can look at the workspace, and Q is 200 times 1. Ah, no, it's only the first eigenvector. Sorry. I need to make help again, because I don't remember. Is a VD. Okay. So I need to make square Q lambda equal A. Okay. Now I go to the workspace, I go to see the dimension. Q is 200 by 200 because it is 200 eigenvectors by 200 entry each. Okay? And then L is the eigenvalues, which is 200 by 200. You know, just so that you get inside, you can say, make the image S of L. You see, they're all along the diagonal. You don't see anything. Let me zoom it. You see, they're along the diagonal. Okay? You see it. You don't see anything. You know, I try to go at the beginning. Sometimes to make it more visible, what I can do is I can calculate the logarithmic. There is. Huh?
Log 10.
No, log is not, you know. There are some small complex numbers. Okay, this is by, you know, by taking the logarithmic of the eigenvalues. You see, the matrix is only diagonal. Okay? So it's similar writing, you know, lambda 1, lambda 2, blah, blah. I think that, you know, first of all, the beauty is that you get practice that the matrix is 2 by 2 matrix is not a matrix. Okay, it's a toy. You see? So 100 by 100 is something that becomes, you know, close to the reality. Now, let's look at the eigenvalues. I told you, you know, I can assign Q equal to capital Q. Then I say I want to choose which one? Number 4. The fourth eigenvalue. No, sorry, the fourth eigenvector. Okay? You see, I'm choosing the fourth column. I assign to Q. And then, you know what I do? I make the image. So I make a Q. Time Q prime. By the way, before looking, go to the workspace and verify that Q is a vector. You see? Lowercase q is a vector. It's 200 entry Q. Right. Now, if I make an image ask in this way, you see the pattern now that I told you. It's very, square symmetric. You see that? Okay, this is a rank 1 image. So that means that that complicated matrix can be decomposed into a set. Now let me rewrite everything, very more, professional. So I can do prime comma 1, for instance, multiply by q comma 1 transpose. Okay, and this is, you see, I put a bracket more. Okay, that's another. So this is the image that I get with the first eigenvector. Okay, so the image, when I write, analytically, A is equal to the sum of lambda I, Q I, Q I transpose, okay? And each one of these is an image. So that means that a matrix A is a sum of images that have the property to be rank 1. And when I say rank 1, you see, it's a smear in that direction and it's similar in the other. Now, you know, so it's a set of images like this one. So this is 1, this is the second eigenvector. Okay? Then you see the third, and so forth. Third, blah, blah, blah. Okay? This is, you know, what I was mentioning before. Okay? So just probably this way is more clear than trying to make the picture that probably I couldn't make. Now, so let's go to the point. Now, these are the data that I was telling you. Okay. Now, and this is before coming. You know, I run this code. Okay. So this is, you know, Apple stocks. Okay. And I use some polynomial regression, which is showing you that, you know, I can make, I mean, a smoothing or a prediction, because my goal is to predict the data. Okay. No, but you know, I don't want to use this one. I want to be available myself. So let's do it. Now, I write everything on the board. Okay. Then we fix everything on the board, and then we transform everything we do on the board into the code. Now, when you have a problem, never touch computer. Don't touch computer. Okay? You are not a computer science. You are data science that, you know, you are developing algorithm. The algorithm has a lot of brain power, and you know, you need to use this brain. So my goal is to predict that. Okay? So these are the training, okay, what usually in data analytics is called training data. So this is the data that you have. Okay? My goal is to make prediction. So what does it mean, prediction? You know, I mean, we will touch the problem of prediction later, okay, in a statistical sense. But before touching the statistical part, I want that it's clear the deterministic part. Because, you know, if it is clear the deterministic, then the statistics at the end you will see, yeah, but it's similar to the problem that I solved. Perhaps, you know, that part will be 1.5 months, probably 2 months. And then you say, oh, but this is similar to the problem that we solved 2 months before. Yes, it's the same. Okay, so let's do it. Now, my goal is the following. You know, I have my data. Okay, the data are ordered in time. Now, it's not theory. This is the problem. This problem, data. Okay, so I'm not talking about the generic problem. It's data. Okay, so my data are ordered in time. Okay, so time, you know, is the day. Now the time, what I did, I mean, rather than having day, I numbered the day, okay? I put the number into the day so that we have the day 1, day 2, day 3, blah, blah, okay? This is just for practical purpose. And if I have a weekend, I jump 2 days, okay? So, you know, the number is 1, 2, 3, 4, 5, Friday. Then Saturday is missing, Monday is Sunday is missing. So I have 1, 2, 3, 5, 8, 9, 10, blah, blah. Okay, so this is a number. Okay, so there is also the problem of a weekend. But you know, as you might say, oh, you need to treat the weekend in a different way. The answer, the conceptual answer is yes, but we forget, right? Okay, so we are making this exercise all together. So my goal is to predict. So what I want to do, you know, is I want to use some set of data. Okay. So this, let's say, you know, this is time Tn. and we want to use a set of t samples, okay, to predict the samples at the time tn plus 1. This is what we want to do. We have these samples, which are xtn. So we have xt1, xt2, xt3. T, you know, t is the absolute time, and n is the index. So, I mean, what I do is this. So, you know, I need to use this data to predict the sample. So, what is the prediction? So, I can predict x. I put some notes just to know to be congruent with what we did. Okay. So I have x at tn, okay, the predicted value, which is equal to theta 1 plus theta 2 t x t n minus 1 plus blah 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 plus theta p x t n minus p plus 1. This is my formulation I'm using. So the predicted value at the time tn is a combination of samples plus theta 1. The reason why I put the theta 1, as you see, you know, it doesn't start from 0, it starts from 600. So if I don't put the you know, the reference value into the data, I mean, I'm losing this part and they go nowhere. Okay, so now, rather than writing this way, I write in the matrix form. So this one is equal to, now, I write with theta, right? Okay, so I write, you know, this is 1, x tn minus 1, and then I have x tn minus p plus 1. This is the vector. And then, you know, I have a vector with theta 1, theta 2, theta 2. This vector is theta, is my unknown. So what I now need to get, I need to know what is the theta that I need to use to combine my past samples to predict the future. Because I'm predicting the value of stocks, Apple stocks, tomorrow, okay? After today, because, you know, after closing today. So this vector here, since this vector is the one that I'm using to xtn, I call it x vector tn. Okay? Now this vector has 1, and then, you know, it's a set of numbers. So now, you know, I mean, so I can do everything here to predict that value. Okay? Now, I can use more data. So what I can do, I can estimate x at tn plus 1. So x tn plus 1, you know, has the same structure here. So if I want to predict the value at n plus, yeah, this is...
That shouldn't be n minus
Right, I
1.
was down correctly. And this is t n minus p plus 1. Okay? So in total is t minus 1, because we need to use, you know, one unknown to model the DC.
Theta 1 is on the left, yes, is the reference. Then theta 2, why did you multiply by xtn minus 1?
Because you know, I need to predict the value here, and then I'm using all the past.
But the one behind it, for example, here for tn minus 1 is theta 2. The value
No,
here.
theta 1 is a shift.
Okay, on the left.
No, it's a shift, it means a vertical shift.
Yeah, it's 600, for example.
Yeah, 600, right.
Then theta 2 is the sample right on its left.
Yeah.
So it shouldn't be xtn minus 1. Because xtn minus 1 is right before tn.
Yeah.
So why
Which
did
means
you-
yesterday. I want to predict, or, you know, I want to predict tomorrow, then I need to use today, tomorrow, today, day before, 2 days before, 3 days
Exactly.
before, and so on.
So it should be multiplied by its own sample. But because theta 2 is for Tn minus p plus 1.
It doesn't matter which order you do it in. It's
Yeah,
just
no.
that's just the renaming of the thetas. You can call theta p, theta 2.
Ah, are you saying that you prefer theta 0, theta 1, theta 2, blah, blah?
No, I'm saying, okay, while it's theta 2, so it should be x Tn minus p plus 1. Because it's far away. It's not
And
just yesterday.
minus p plus 1.
Yeah, but for theta 2, theta 2 should be multiplied by this.
Why that?
Because it's far, it's
Because
not
I'm
just
using all the
yesterday.
samples. I'm using all this. I mean, is it you or someone else? Because you know, if it is only you, I can discuss with you later. But if it is someone else that is in doubt of what I'm using, so these are the data. So
I think he's saying that the order of the theta should be useful.
Exactly.
Cioè, theta 2 si riferisce almeno dipende se si riferisce al valore all'istante più lontano. Cioè, se theta 1 è il valore all'istante iniziale, theta 2 dovrebbe riferirsi al valore più lontano del tempo.
ma io posso nominare come voglio.
No?
You know, the name I can give you theta is completely arbitrary. I can sort the data as I want, as far as I keep a consistency across the problem. Is it this one?
We'll discuss after.
Okay.
Okay.
So, I mean, I can call it theta 0, theta 1, theta 2, or I can call it theta 1, theta 2, blah, blah, blah. I mean, it doesn't matter.
But on the map, for example, theta 1 is the left and
Yeah, but I mean, I order because this is now, this is, you know, this is my past value. This is my past at the time 1. This is my past 2 times. This is my past, or I don't know. This is 1 day before, 2 days before, 3 days before, 4 days before. Okay? That's why, you know, I say 1 day before, 2 days before, 3 days before. So in principle, you know, I mean, I can put the theta 0, then I have theta 1, 1 day before, theta 2, 2 days before, theta 3, 3 days before. Then I have a problem that I need to call this one theta 0. And MATLAB doesn't like 0. Because the pointer, there's no possibility to point to 0.
but you're looking for these thetas.
Yeah, my goal is theta.
Okay.
I can,
Uh-huh.
you know, as far as I keep the consistency across the problem, I can number
Okay.
as I wish, you know. Okay. But you know, I really could not understand if you didn't tell me, you know. It was okay. So this is my data, huh? And this is a set of vector about the past that I'm using. But since I have the data, because you know it's on the training, that I mean I know this value. Okay, I know exactly this value. So I mean, what I can do is that I can minimize the error. So my goal is that I can look for data such that this error is minimized. But you know, I can repeat the procedure many times with all the samples. So I move forward. Then I can repeat the same as x hat Tn plus 1. Because this is applied on the training samples, which means the data belonging to last year, 2 years ago, 3 years ago, okay. Because you know, these are the training samples here. Okay? So this is the behavior coming from the past. Okay? So I know this one. Okay, now. Yeah. Like here, you see? So if I go here 5 years, these are existing. Okay? So I use this one for training. That's what I'm doing. So so I take, you know, so I move like, I don't know, this index can be 1 year ago. Okay? So I'm using, I don't know, an interval of time, that might be 3 weeks, to predict the value that is last year. Then I can move 1 day forward, which is 3 years back plus 1 day. 3 years back plus 2 days. 3 years back plus 3 days. 3 years back plus 4, blah, 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 and so on. Okay? So this kind of operation that I'm doing is inserted within a certain time interval, which means, I'm here, I try to predict this value, but I have this value. So this goes into my set of equations, okay? So then I move forward, and so on. Now, so I repeat this procedure, then, it's this one, then I have a vector, Tn plus 1, I call this way, time theta. Sorry, this is just one. Okay? So what I do now, now that you understood this trick, what I do is the following. I have, a set of measurements, which might be x Tn, x Tn plus 1, x Tn plus n. Okay? So this is the set of values. Actually, I'm predicting these values. Technically, I'm predicting. This predicted value is equal to, so this is by choosing a set of vectors, so it is x vector Tn, which is, a row vector. Then it's the second one, x transpose Tn plus 1. Blah, blah, blah. And then I have x Tn plus n. Everything multiplied by theta. Theta is my unknown. Okay? Now, this problem is becoming, this is a big matrix X. So this one, is the predicted value of y. So y is equal to x times theta. So this one, is m times p. This is p times 1. And this is one is m times 1. Always put a dimension in every problem. Okay? So that means essentially that I'm using a set of segments, which is m. M can be 10, 20, 50, 200, doesn't matter. Okay, so I use a set of segments like this one. I take all this data to predict the next. I move forward. I use all this data to predict the next. Move forward. To all this data to predict the next, and so forth. Clear? Okay? But I know the next. Because it goes into the training set, which means I know the data. Right? Okay, so what I indicate as y actually is existing data. Okay, so this is the problem I need to solve. So I need to get the data. Then I know, in order to get data, what I can write the least square problem. And the least square problem we solve, okay, is the following. So if I want the theta n, okay, which is the one that I need, is obtained as, you can look at your note, is x transpose x, this x, to the minus 1, x transpose y. Okay? This is my estimator. So if I put this one, and then I can predict. Now, the job is not finished. Tell me.
But is there a method to understand what is the optimal P to choose?
Yeah, okay. So, the job is not finished. Because when I say this is, this is theta, I don't have any number. Because if since you are an engineer, you need to say, I get theta within an accuracy of. Okay? This makes the difference between if you write a code or if you write an algorithm. If you write an algorithm, you need to give the uncertainty. Because the people want, when they give you the money, because they are investing, they want to know if you say, if you say invest, you need to say, you can invest, but I give you the data with these degrees of uncertainty, okay? So, you need to have the uncertainty. Now, how can I get the uncertainty? Now, the way to get the uncertainty is this one. The error here is y minus that, okay? So this is the error, right? So this is the error in estimating. This is the error in predicting. Actually, we are estimating the value of the stocks at a certain time. So we are now estimating the parameter. We are doing estimation. Okay, you don't know, but we are really doing the estimation. Now, so that's the error. But we can calculate the error on the data that we have, because we can get the confidence on the data that we have. And then, this is the vector. Now, this is a set of n errors. So what I need to know, I can get, for instance, the square error. What is the square error? I can get epsilon transpose epsilon. Epsilon transpose epsilon is the sum of the errors. If I want to know the mean square error, then I divide everything by n. Okay? Because I'm summing now, this error is a vector with n times 1. So when I do this way, this can be written as a sum of epsilon I squared, I going from 1 to n. But then I need to divide by m to get the mean square, because it's a mean. If I calculate the root square for that, I get the uncertainty degree. I don't know, you get the accuracy of the value plus minus, I don't know, an error of $0.50. Okay? So if you have two people, one that is selling you a system with an accuracy of a plus and minus $0.50, and the other plus minus $10, which one you choose? Okay? So that's your job. Your job is to give is not to write the algorithm. You don't need a genius to write that. What you need to know is to give a parameter of accuracy. You need to know, you need to give, the degree of mismatch. Or you can optimize the predictor to the specific problem, as it says. Okay? Now, but first, let's start with this. So remember this formula, because I will use that. Okay? I will use this formula. Now, it's a pity that I need to cancel. Okay? Probably I have a note. So, let's try it here. Okay? I use this small because what I want to do after, I write the code according to that. Okay? So, now, how is this one? Okay? So, what I want to do is assume that I calculate the optimum one, which is this one. Okay? What is the error for the optimum one? Now, the way to do is I take this one and plug into there. Okay? So if I plug into there, I have the optimum error, that is y minus, sorry, I'm shrinking, x, then I have an x transpose x to the minus 1, x transpose y. Okay? So, if I want to get the optimum mean square, I need to take this one multiplied by epsilon transpose epsilon. Then I get the value of the error, or the mean square error, at the optimum combination of the coefficient theta. Now, after that, I can play with the p parameter as is suggesting. Okay? which it makes sense. Because everything is for a certain set of parameters, p. So what's happening if I make a p long, I don't know, 1 year? What's happening if I make a p long 1 week? You see? So I can make a short-term prediction, 1 week, okay? Which is, you know, it's very quick. Or I can make a long prediction, okay? Now, so this makes big difference in the stock. So, you know, that's the stuff. Okay, so I start with this one, huh? Now. Any comment before? Now, I have only my notes. So my notes should be similar. Let me see, let me see. Okay. Yes. I have. Okay. Let me cancel from the workspace, you know, the matrix A, B, L, Q, capital Q, because you know I don't need it. Yeah? So this task is finished. Okay. Now, let me see. I don't remember. The value should be, so the Apple stocks 1 should be the time, and the Apple stocks 2 should be the value. Let me see. I make a quick plot just to be convinced. What is the name? Apple stocks, right? Stock, singular or plural? Singular, stock. So it's 1. And then I copy. This is only to verify. Okay, yes. Okay, this is the time. Apple stocks 1 is the time. And Apple stocks 2 is the data. So my data I'm using is the data of the second column of the matrix Apple stocks. Okay. So let me call this one as a T. So T is equal to Apple stocks 1 because it's the time. And the data we call X, right? X. X is just so that the variable, you know, is too long. Okay, so I cannot do it. Okay, so X is the, you know, is similar. So time is there, X is the same. Now, you know, I want to know what sample, I don't know, I can make my training using not all the data, but perhaps, you know, I can use this part, okay? So I want to know what time index, so what n is that? So in order to see, you know, I go on the plot, and then I see, I don't know, I start from here. So this one is the index, x is equal to 1383, so n, starting n is 1, let me write it. 1383, let's make 1300, simplify. Okay, and how long is that? 1500. Okay, so I don't know, we can make 1500, we can make 300. Okay, so we use 300 samples. We can use less. Okay, so n starts with 1300, and n plus m is 1500. Okay, so n is equal to 100. Okay, so we use 200 samples to train. So we use this in this time interval to train the system. Okay, I don't know. We can make it longer, but anyway, we start with something. Okay. Now let's go to the code. So you know, let me remove this. Okay. So we say m is equal to 200. Right. Now I prefer to write parametrically, and I recommend to write parametrically. Which means if you write parametrically, you can change any time. Okay. And then I choose p equal to, I can choose p equal to 20. Okay, so we use 20 time samples in the past. Okay, so this is the size of the problem. Just to know. So 20 is input in the past, which means I'm using. Yeah, it might be even longer, but, so let's start with 20, okay? Now, so the issue says, first of all, window the data, because that one is safe. If you want to predict x at Tn, okay, you need to use all the samples in the past, which is Tn minus 1, blah, blah, blah. So what I need to do is, I need to write the for cycle for index k, okay, which is going from n. Now wait a minute, I am on n. I want to iterate, and I want to use. Okay, so I go from n to n plus n. Now what I do is, I want to assign to x that value, okay? So x in a matrix, so we write directly the matrix, so that is a row. Okay, so x, now, this one is the row number 1. So when I'm using the allocation on n, I am assigning to the first row of this matrix. When I am writing the second row is for n plus 1. So the row is the value of k minus. Let me do it. It's a value of k that goes to n minus n plus 1, comma 2 points. Okay? So this is the vector. Okay? So this is the row vector. This row vector in the matrix is coming from a vector that contains 1 in the first position. And then it contains all the data which come from x, lowercase x. Remember, capital X is the matrix that I'm creating, and lower x is the data, the true data. Now the data are from, now I am okay. So it is n. I'm predicting n. So I'm using n plus k to n plus k oh, it's negative. Okay, it's n minus 1, so it's n plus k minus 1 in n plus k minus p plus 1. Now it simplifies. Okay, so this should be So what I'm doing here is I'm sitting. Okay, I wrote it so I can cancel that. Okay, so I'm sitting. So this is the data. I'm sitting on the time sample that is n minus k. Okay, k is going forward. So this is, sorry, it's n plus k. It's going forward. Okay, I need to predict n plus k. In order to predict n plus k, I need to use this data. And these data are n plus k minus 1, and it is n plus k minus p plus 1. This is what I'm doing. Okay? Then at this, I multiply by theta. I hope I didn't do any mistake. Okay, this is x. Tell me.
I think you should write x with index of n minus, for example, p to x index of n.
No, because I'm sitting on m.
Yeah.
Okay. This index, this is the big matrix. This matrix should start from 1. I can write it separately because okay, this is the x row. So I'm sitting on a sample and
See, you are on the sample of n, then you need sample n minus p to n.
n minus p to n, sitting on n. So k is n already, you're saying. Because I'm sitting on.
I think you should be index because it depends more index.
So when I'm sitting on, when I am on k equal n, I'm reading n minus 1, n minus p plus 1, which is what I want. You know, for instance, let me check it. Copy this. And I copy this one. This temporary assignment. K equal n. Oh, a bracket. The bracket is missing. And next row. White one.
You should index it.
Y is one. Because x is not a row. X is a column. Okay. These are typical problems. No? Then I should put punto virgola.
Excuse me. You are going down bar. P is positive. You are going, for example, from 100 to 19. It's incorrect.
Say it again.
You should write k minus p plus 1 to k minus 1. Change this to in the. Now you're going from k minus 1 to k minus.
Because it's negative. Okay, I change because there is written differently.
But you can do k minus 1, colon minus 1, and then you go.
Yeah, it's negative, and then I extract only one sample. K minus P plus 1 to K minus 1. Yeah. Now they are column. Let me see, this is a column, I put in row. Okay, now should be okay. Why this time? Okay. I need to do this way. I made a mistake about the time axis. So it's plot. Okay, the data doesn't go. The data goes up to 1,300 because this is in samples. So everything is mapped back. So this is 900 and this is 890. This is 900. Okay, so it's a 20. Okay. It's a row wise. Good. We managed. So X row is the row, and then I assign this one X row. Okay, every row. Then I build X in this way. Then I build Y, which is equal to X. Now I am in K minus 1. This is K. Okay, this way I created the matrix X. Which is now I go there and I see the capital X is 201, which is the dimension of M times 20. Okay, which is M. Sorry, but there's one sample missed in addition. Okay, so I choose 200, but I go to 201 times P. Then I have 201 in Y. What is Y? Oh yeah, I forgot. This is M K minus M plus 1. And K is equal to, okay, blah blah. And Y is equal to 201. Okay? Now y is, actually y should be a column. So what I do, I transpose. I make y a y transpose. And this one, in this way, y is exactly the size that I need. Now the theta that I'm looking is equal to, now I copy. Okay. Now that operator there, is called pseudo inverse. Okay. So let me see if I can get it. L pin. Pin stands for pseudo inverse. Okay. So it is, here. Okay. So it is XAX. Where is it? Pseudo inverse is A. So it is. Let me calculate as y right there. So it is the inverse. Oh. It is x transpose x. Capital X prime multiplied by x. So this way I calculate the inverse of x transpose x. X transpose x multiplied by x prime multiplied by y. Okay, this is the theta that I mean. This theta, which is this value, okay, this is the theta, okay, the 20 values that, is telling me something. But, if I look at the values, the numerical values, except the first, that is 23, for some reason it's 23, the others don't tell me anything. So in order to have an idea of the error, what I need to calculate, I need to calculate the error in this case, which is the optimum, which is up there. Okay? So rather than computing, now I calculate everything, so I can calculate it. So the optimum theta is that one. Now what I need to calculate is the optimum. So I copy it here again. The optimum one is y. Okay? Then I collect the y. I group the y. Let me calculate this way. Is identity matrix minus x transpose x to the minus 1 multiplied by x transpose everything multiplied by 1. Okay, this is the optimum. Then what I want to get. I want to get epsilon transpose epsilon at the optimum. So for the best case. So for epsilon optimum transpose epsilon optimum. Then I need just to plug in. So it is y transpose, then it is all that transpose multiplied by that one multiplied by y. Right? Now, so this is transpose. Now, one simple and stupid way would be to calculate the epsilon and then, see if, what comes out. Rather than do it this way, I try to manipulate the matrix by formula, by hand, until I come out with something that is more manageable. Now, so this matrix, which is identity minus all these matrices, okay? Now, if I multiply this matrix has a very special property, it's called the projection matrix. So that x multiplied by x transpose x to the minus 1 times x transpose, this matrix is called projection matrix. That will be discussed next time. But the projection matrix P has a very nice property, which is in case I multiply P by itself, it comes to the same matrix. So P multiplied by P is equal to P. This property is called idempotent, which means the power of a matrix is the same. Okay? So now, if I consider these projection matrices and I manipulate here, so it comes out, you know, that I have a transpose. So if I calculate transpose here, this goes there, this goes there, then I transpose, so it's the same. Okay? So as a result, you know, I continue by considering this property, this y transpose, then I have identity minus p, then I have identity minus p, okay, and then I have y. Now, you know, I can calculate. So I have identity times identity, which is identity. Then I have minus projection. Then I have, you know, it's minus projection again. Then I have a minus 5 plus projection to the square. But since for the property of projection matrix, this one is equal to p. And this p simplifies with that. So it's again identity minus p. Okay? So that one is another property that we will see next week. Okay, so then at the end of the week. So, I mean, if I continue this way, the total error, which is what I want, that's an optimum, transpose, that's optimum, is equal to y transpose identity minus p y. Okay? Then I implement this one because it's more compact. Or another way that I can implement the following: y transpose y, because you know I can multiply y transpose with the identity, and then I can multiply y with identity. And so that comes y transpose y minus y transpose p y. Now this formula is relevant in the case when you want, as your colleague was saying, to optimize the predictor. Because if you want to optimize the predictor, what you want to do is, I try to do as much as I can with the data that I have. I try to minimize the error as I did. Then what I do, I want to find the value of the parameter which is hidden here in this capital P. So what I want to do is to minimize that. But if I want to minimize that, I can maximize this term. Because this one does not depend on the parameters of the program. So that's another way. So I can maximize this one with respect to lower p, which is the length of the predictor. Okay. Now let's go to the here. This is theta, okay, let's say. But you know, if I want to get the mean square error, okay, then the mean square error is equal to, now, as I said, okay, let me calculate the projector matrix. So P is equal to x times mean of x prime multiplied by x, close the bracket, times x prime. Okay? This is the projection method. Then you know I'm here, I have y. So the mean square error is y prime multiplied by y minus y prime, I'm reading there, so you read there, multiplied by p, multiplied by y. Now, since I want to divide by n, because I want the mean square error, you know, is the mean, so I close within the bracket and divide by n. Okay? So, now let's calculate that and see. Did I make a mistake? It's not on theta, it's on projection matrix. No? We calculated theta before. Am I wrong?
Maybe you could say the script and run that, and then it will tell you where in which row is the error exactly.
Okay, but you know, I don't think it doesn't change much. Say, let me say here, okay. So is line 16. Yeah, the last one. Ah, it's y prime time. You are here to see me. You need to control me. Okay, that's the mean square error. So the mean square error, which is in one number, is 310. Okay? So the square root, which is, you know, usually people like the square root. Now it doesn't like. Okay, because I made a y prime. Yeah, 17. So I don't know if we, it seems too big, honestly, okay? 17 as $17. So my error is 17. Let's make the predictor longer. I don't know. Let's make 80. I need to clear the variable, but I cannot clear all because I have the data. Let me see. Okay, is 15. So if I make a predictor longer, it's predicting better, okay? In the mean, on the data. So I can make a training on more data, which is n, I'm using n. So you know, I can use, I don't know, from 800, and I can use 400 of data. It's increasing, okay? So that's, I mean, unless, you know, there is a mistake, I can use, for instance, I can make a predictor longer, with a longer set, and it's still 17. So it seems that, you know, 17 is a physiological. But, I mean, it seems too big. But anyway, so that's, probably it's these fluctuations that are destroying the capability of the predictor. Okay. You can make a predictor shorter. You can make a predictor on the order of 1 week. Because you know, Apple stocks are very chaotic. 19 with a predictor 8. So if I make a predictor 8 is 19. If I make 20, so if I make 100 is 17. I mean, there were a number, what was the number when it was 15?
20.
20?
70.
20. Okay, so I know. Then I give you the code and you can play with this. So what I did here, okay, this is the style that I'm doing. So I flip here and there, okay, with the conceptual part, what that I'm creating and building, and then I put it to the code. The philosophy is, the philosophy, you know, the message is never touch the code before developing what you want to do. Okay, and then that means that when you go to the code, everything is well established. You don't find any trouble, okay, unless you know the transpose or similar, okay, which is something that happens. Let me just look at a very curious stuff. P is I told you, is a projection matrix, no? So let me calculate the eigenvalue and the eigenvector of P. Okay? Now, so we remember, you know, it was Q, comma, L, right? And it was A of P. Okay? Now, let me calculate that. Okay, L are the eigenvalue and Q are the eigenvectors. Okay. Now let's see what are the behavior of the eigenvalue. So if I make a plot the arc of L, I extract the diagonal. Okay, now look at that. So these eigenvalue, okay, and the absolute value, because there are some complex numbers. Okay, these are the eigenvalues. Okay, so the eigenvalues are 1 or 0, right? This is 1, you know. If I look at there, this number is 1. And then all the other values 0. Right? But you know, think about that. The projection matrix says the projection say is idempotent, right? I said. Okay? So you can multiply P multiplied by P and is equal to P. Okay? Now, what I did, I calculated the eigenvectors and eigenvalue. So that means that, you know, this P is Q lambda Q transpose multiplied by Q lambda Q transpose. Okay? Now, you know, Q transpose, this is identity. Okay? So I have lambda, so it's lambda square. So I have a Q lambda square Q transpose. Okay? So that one is Q lambda square Q transpose. But this one here is Q lambda Q transpose. So you know what's happened is that lambda is equal to lambda square. But what are the eigenvalues such that the power is equal to itself? 1 or 0. Because if I make 1 to the power of 3 is 1. 1 to the power of 2 is 1. 1 times 1 is 1. 0 times 0 is 0. So, you know, we have seen that the eigenvalue of the projection matrix are always 1 or 0. Which is, you know, something that probably will be helpful one day. Okay? So, that's today. That's all for today. That's me. This is when I said, you know, it's going to take a little bit of time because, the code does not go directly. Nice, first shot. Okay? So, but I believe it's beautiful. I don't know if you like the style. Okay? If you like or not, let me know. See you Friday.